Now let's just see few theorems which are like intermediate value theorem or Rolle's theorem, or there is one more theorem which is called Lagrange mean value theorem. So let's just see this theorem, which is first theorem, which is intermediate value theorem. So what does it say is that if there is a continuous function and on a closed interval AB it is a continuous, then if D is in between FA to FB, then there is a number C such that FC equal to D. If you have something like this, right, where this is FA, okay, this is, let's suppose, FB, and then you are having any point D, then there must be C. This is A, this is B. There must be C in between A and B such that that is FC equal to D, right? There must be C. And that's very obvious from the diagram itself. If this function is continuous, then it must like this D must be passing through the cutting the curve at certain point. Okay, cool. So that's what this theorem says. But this theorem we will be using for some other purpose. And what is that purpose? We will be saying that if FA into FB is less than 0, which means that FA and FB are having opposite signs, which means this is A. Okay, I mean this is what FA is, and let's suppose this is what FB is. So FA and FB are having opposite signs, either this thing or maybe FA is positive and FB is negative, something like this. Okay, so let's suppose this is A, this is B. If FA and FB are having opposite signs, then it must be cutting somewhere the x-axis, which means then you can say there exists a C such that FC equal to 0, right? Can there exist multiple C's? Yes, there can also exist multiple C's. Okay, because it can go something like this. It can go something like this. There can exist multiple C. So I can say there exist at least one C. And that's what the theorem says, right? There is a number C. I mean, there is at least one number C that satisfies this. So maybe we can directly have the questions here. So let's suppose we want to prove that this function has a root between this -2 and 2. So can you prove this? This is continuous because this is a polynomial function and polynomial functions are continuous. Then if you check f of -2, it will be 16 minus 8. It is, I think, greater than 0. Okay. Sorry. Yeah. I mean, f of -2 is greater than 0, but I don't think it will help. So can you solve this question? So they're asking, it has a root in this interval. So see, f of 0, if you check f of 0, then it is negative -4. F of 2, then it is 16 minus 6. It is 10. So it means there is a root between 0 to 2. There is a root between 0 to 2. So it means there is a root between -2 and 2 also. And similarly, you can say that I think there is one more root, right? F of -2 is also positive, I think, right? 16 plus 2, 18 minus 4. I think this is also 14, right? So similarly, you can say there is one more root between -2 and 0. So at least 2 root you can guarantee by just the observation. Is this okay to everyone? Yeah, at least 2 roots in between -2 and 2. Okay. Cool. So I hope that is fine to everyone. Now let's just see this question, which I have taken from University of Texas. Consider the function fx, which is defined to be 0 if x is equal to 0, which means it is 0 if x is less than or equal to 0. It is 1 if x is greater than 0. This is something like this, okay? Which means, like, I think till this point it is 0, and then till 0 it is 0, and then it suddenly become 1, something like this. Okay. Now what they're saying, why doesn't this contract? So they are saying f of -1 is 0 and f of 2 is 1, right? So never takes the value 0.5. So which means, let's see, f of 0, f of -1 is 0, f of 2 is 1. Now what does this intermediate value theorem says? You take any value between this f of a and f of b. Let's suppose you take the value 0.5. So there must exist some constant which is actually equal to 0.5, right? This is what intermediate value theorem says. But actually this is not true for this function. Why that is the case? There is no value c such that it is 0.5 because it is not contiguous. Yes. So it is not true for given function. Given function. And intermediate value theorem is not applicable. Because function is not continuous in this range. Okay, function is not continuous, that's why this is happening. So this is the answer here. Function is not continuous. Let's just see this question. So what they're saying, the equation x power 7 plus x minus 1 equal to 0 has a solution in 0 to 1. Maybe you can do this at your home, right, as an homework. That is easy question. I have the solution on the next page. Okay, so you can do this also as an homework. Okay, I have the solution on the next page. Now let's just see the Rolle's theorem. So this theorem is very intuitive also. This says that if you have 2 points where f and fb both are same, the function is continuous, right? Then continuous and differentiable, then there is a number c such that f dash c is equal to 0, which means they are saying that if we are having f and fb same, which means you are having fa here and fb also same. So which means that the fb is, I mean, it is returning to the same value. So fa and fb both are same, then there must be some c such that this f dash c is equal to 0, right? So maybe something like this, or maybe something like this. So you can say that here this is A, this is B. See why I'm doing this. I mean this in little hurry because that is already there in the in the videos, right? So you can say like here the multiple C's are there, right? Multiple C's are there. So here f dash C is equal to 0 for multiple points, right? Okay. Okay. Now let's just see this particular question. So they are saying f3 is equal to 2, f dash 3 is equal to 1 by 2, f dash x is greater than 0, f double dash x is less than 0. Okay. How many possible roots this f has? Okay. At 3 it is 2. Okay, this is f dash 3. Okay. At 3 it is 2. It is always increasing. They are asking how many roots does this f has? And then function is, oh yeah, this is a good question, right? Function is concave down. Function is always concave down, right? Okay, that's really a nice question. Do you want to solve this? So what they're saying, function is always concave down, not at just one point. They're saying for all x it is concave down. If the function is concave down and function is always increasing, then I think they are talking about this particular area, right? Function is always increasing. They are always talking about this particular area. How many roots this f has? If the function is always increasing, then which means that they are saying that the other possibility does not exist. Then it can have at most one root, right? It can have at most one root. But the only thing is to prove whether it is or at most one or exactly one. That's what we need to prove, right? See, the function is always increasing. That's the point. Yeah, it should be exactly one. Why that is the case? See, this is the area in which we are, right? So the function should be something like this only, something like this, always something like this. This is the area in which we are. The function is always something like this. Maybe it is a graph of log x or something like this, right? So basically, like I mean, you can argue by looking at the geometrical interpretation, or you can argue with the mathematical interpretation also. You are saying that f3 is 2, and since the function is always increasing, can you tell me it is strictly increasing? Remember, can you tell me what is f3 minus, which means just before 3? It will be 2 minus, I mean, just less than 2, because it is always increasing. Remember, okay. See, if f3 is 2, then before 3, it must be lesser than 2. Must be lesser than 2, isn't it? Is this okay to everyone? And even before that, it must be lesser than that value, or even before that, it must be lesser than that value. So basically, somewhere it will, like this f is 0 also, right? Somewhere f is 0 also, because it is always increasing. So if you go in the reverse direction, if you just look at the reverse direction, I mean, see, this is f of 3, but there must be some fc where it is 0, क्योंकि 0 से ही 2 आया होगा ना, बूंद बूंद करके भी तो घड़ा भरा होगा, मतलब कहीं ना कहीं that must be 0, because it is always increasing, and it is somewhere it is negative also, somewhere it is negative also. Basically the function is something like this, क्योंकि नेगेटिव से 0 आया होगा, 0 से 2 आया होगा, क्योंकि इंक्रीजिंग है. द फंक्शन इज ऑलवेज इंक्रीजिंग. दैट्स द प्रॉब्लम, आई मीन दैट्स द पॉइंट, right? So let's see the explanation that they have. The function have at most one root. Okay, so first they are saying it has at most one root. If it had two roots, the Rolle's theorem would mean that f dash x equal to 0 for x between okay. They are still saying at most two roots, at most one root. They are not saying exactly one root, right? But we are arguing that it is exactly one root. I mean, there is not a possibility that 0 roots exist. नहीं, ठीक है, डोमेन तो मतलब, हाँ मतलब that is also okay, but domain we should be assuming the real number. It's not an issue. But I think in this case it should be matlab exactly one root. There is not a possibility that it can have 0 roots. There is no root at all. It must be touching somewhere this x-axis, right? If somewhere it is 3 and it is always increasing, तो कहीं से तो आया होगा ना 3. It must be somewhere 0 also, according to me. Okay. Now I hope that is fine. Now let's just see sketch a possible graph for f. So as I said, like this could be the possible graph for f, where it is always increasing and it is concave down, right? This is the possible graph for f. Okay. Maybe it is a graph of log x, right? It is a graph of log x, and if you take the differentiation, it is 1 by x. So maybe you can just adjust the constant, this 1 by 2 by something like this 3. So it is 1 by 2, 3 by 2, right? So maybe it is a graph of 3 by 2 log x, because if you differentiate it, it will be 3 by 2 into 1 upon x, and then if you put x equal to 3, then it will be 1 by 2. So it is satisfying this condition. Okay, but it is not satisfying this, right? Yeah, anyway, like you can adjust the constant. Maybe you can take the two constant, maybe log x plus I mean, you can make an equation like a log x plus b, and using that equation you just find out the values of a and b such that it satisfies these two things, and then we finally have the answer. Anyway, like I hope you got the point. Like roughly the graph will be something like this, right? Something like log x. Is this okay to everyone? Okay. Now you are getting little more intuition than you already had about this calculus. So basically, especially about this part, that if these two things are given, then how to interpret this, right? Okay. Now let's just see this question. So we will be solving now questions where they will be asking about the exactly one root, about exactly one root. So do you remember how to solve these kind of questions about exactly one root? So we will be taking the help of f dash x. So what will I say that I will say that, okay, for some value, can you tell me for some value, uh, maybe f of maybe -5 or something. So for some value it is less than 0, maybe f of +5, it is greater than 0. So there is at least one root is guaranteed, right? At least one root that is guaranteed. But we want to check whether it is exactly one root or not. So how to check exactly one root? So at least one root is there, but using the f dash x, you can check whether it is exactly one root or not. So f dash x will be 2 plus e power x. Since it is always greater than 0, function is always increasing. Since the function is always increasing, you cannot cut down, you cannot come back, right? You cannot decrease. So exactly one root. Okay, it is at least one root, and then that's how we solve it. So for the exactly one root, we take the help of f dash x. Okay, so we take the help of f dash x for exactly one root. I hope that is clear. Now, similarly, you can do this question. This is a good question. You can do as an homework. You want to prove that there is exactly one root, okay, unique root. How to prove it? Using the f dash x. The solution is on the next page. Don't worry. So you can easily do this question. Okay, trust me. Now let's just go here. This is little good question where they are saying that you have a function and it has a 0 between x of -1 and 1. Okay, so basically show that you want to show that this function has a root between -1 and 1. Can you show? And then they are saying, be careful. This function is not continuous at this 0. So function is not continuous in this range. If this is continuous, then I think you can easily prove it, right? At 1, it is greater than 0. At -1, okay, at -1 also it is greater than 0, right? Sorry, it is 1 upon e -1. No, at -1 it is less than 0. And at -1 it is less than 0. At 1 it is greater than 0. So if it is continuous, then you can do it. You do using the Rolle's theorem. But it is not continuous. But still, can you play some trick? That's what they are saying. You are getting my point? What is the question here? If this is continuous, then you could have done using the Rolle's theorem, but here it is not continuous. So what to do? Okay, I also don't know. Let's just see. It is negative. See, at -1, it is less than 0. That I completely agree. At 0, it is not defined. That I also completely agree. But 0 से just पहले क्या होगा? This is here negative. 0 से just पहले, I think this is a huge number. Minus infinity, right? 0 से just पहले here minus infinity. Okay. 0 से just after 0 it is plus infinity. Then it is dropping the value negative to positive. It is changing from negative to positive in between -1 and just before the 0. This is 1 upon x square. If I increase the x, do you have any idea? Value check करेंगे -1 से 0. Okay. if I increase the x here, I mean, this is x square. So 0.5 is actually lesser value, right? This will decrease. This will keep on more decreasing. Okay. This will decrease. And since this is 1 upon e power x, and I'm putting the value, let's suppose minus 1, 1 up, okay, 1, and then if I put 0, it is increasing, it is decreasing. Okay. Have you got some idea? Let's just see the solution. I think we need to check some values here and there. So let's just check the solution. So they're saying, note that f0 is not defined, f is continuous. Continuous everywhere, everywhere it is defined. Okay, except 0, it is continuous everywhere. But the intermediate value theorem requires f defined on the entire interval, else it can still jump. Okay, anyway, we have f minus 1 less than 0, f1 greater than 0. Note that limit x tends to 0, okay, minus infinity. So just a second, x tends to 0, which means, okay, here also it is minus infinity. Is this? If you put something greater than 0, so it is minus. Yeah, sorry, I did this wrong. So here also it is minus infinity. Okay, तब तो हो गया ना, फिर क्या दिक्कत है? So you can take the range which is 0 to 1, right? You can take the range which is 0 to 1. So it is negative, and at 1 it is positive. So you can say that that it is continuous between any value. You can say 0, 0, 0, 0, something like this, right? And then 1. It is continuous between this interval. So there must exist one root. Okay. So something 0.01 you can take, and there must exist some root. Okay, cool. Sorry, I did this wrong. So it should be minus infinity only. Because they are saying limit exists. Because it is x tends to 0, they are saying it is minus infinity. Either you go from the positive end or you go from the negative end. So that's what it is given to us. That the limit exists. Yeah, yes. Okay. Now let's just see this mean value theorem. Okay. So this is also known as first mean value theorem, or it is also known as Lagrange mean value theorem. So either you call it a first mean value theorem, Lagrange mean value theorem, or just mean value theorem. First mean value theorem maybe because it is involving the first derivative. Okay. So it will involve the first derivative. That's why probably it is called first mean value theorem. Cool. Let's just see this. So what does this mean value theorem says? That suppose f is continuous on a to b and differentiable on a to b, then there is a number c such that this happens. So what they're saying, that if it is continuous and differentiable between a to b, let's suppose this is a, this is fa, and there is some value b, and this will be fb. Okay. And then they are saying, if it is continuous and differentiable in this particular interval, now you can have any function, something like this. Then there must be a point C such that there will be a line joining these 2 points, isn't it? What is the slope of this line? What is the slope of this line? Whatever is written here, right? The slope of this line is fb minus fa upon b upon a, b minus a. This is the slope of this line. Now what they're saying, that if you take the slope of this line, I mean the line that you're talking about, which is this, if you take this line, and if you take a tangent on some c in between, okay, maybe the function is something like this, then tangent on some c, maybe here, then this tangent at some c is parallel to, so this is the slope at c, this is the slope of the line joining a and b, right? These two are different slopes. So they are saying, if you are taking some point c in between a and b, then at the point this, I mean, there exists a point where this slope at this point and slope of the line joining a and b both are same. So what I'm saying, let me go to the next page. Suppose you have something like this. this is A, this is B, right? And then, sorry, let me draw something like this. Yeah. Suppose this is the function that you have. And then I say, you draw a line, you draw a line which is joining A and B, something like this. There will be a slope of this line. Then they're saying there exists a point C such that the slope on that point, and these two lines are parallel actually. The line which is joining A and B and the tangent at C are parallel. So that's what they're saying. Okay. Okay. So they are saying the tangent at C and the line joining A and B are parallel. So there exists a point C. Cool. So basically, mathematically, the equation is something like this, that if you have A and like a function which is continuous between A and B, then this exists. There is a point C such that f dash C equal to fb minus f upon b minus a. So I'm just trying to understand this intuitively. Okay. Suppose that actually I'm not sure if I can frame an example here, but let me just try to give you an example. Suppose you are going from a place to another place, okay, and suppose the distance between these two places are is something. Let's suppose the distance is 100 kilometers, and if I give you the time that you have reached in 4 hours, okay, then can you tell me the average speed? So basically, this is, let's suppose, a point 0, a coordinate 0 or something, or this is 100. So you will say the average speed was 100, and whatever the relative distance I'm taking, 100 minus 0 upon 4 hours, right? It is basically 25 kilometers per hour. Kilometer per hour, isn't it? You will say that this is the average speed. I mean, on average, you have taken this thing. Is this okay to everyone? So what I'm saying that this speed is average. Like you have 100, you have covered 100 kilometers in 4 hours. It means on average you are running. I mean, if you run with the constant speed of 25 kilometer per hour, then I think you should be reaching in 4 hours this 100 kilometers. Okay. And what is this f dash c? This f dash c is speed. So if I just measure this f as a distance, then this f dash c is basically speed at c. So basically they are saying that your average speed, whatever is your average speed, I mean, there must be a point where, see, if you're running at 25 kilometer per hour, then tell me, are you always running 25 kilometer per hour, or sometimes less, sometimes greater? Sometimes less, sometimes greater, right? So there is a point C where you will be exactly matching this 25 kilometer per hour, which means sometimes you are running with the lesser speed, sometimes maybe more speed, but there is a point C such that this f dash c is exactly equal to this average speed. So basically, this is also called as average slope. Average slope. I mean, there are slopes at every point, but if you take the average of all of these slopes, then you will be getting fb minus fa upon b minus a. This is the average slope. So, I mean, intuitively you can understand like this, that there is an average slope, I mean the slope here, and if you find out the slopes at every point, then there must be a point where at that point the slope is exactly equal to the average slope. Yeah. So basically something like that you can understand. Like you don't need to worry about it much. But yeah, I just tried some intuition. Actually, in the gate, they don't ask these things much. So that's why I don't want to spend much time. So maybe we can directly see some questions and you will get to understand that where to apply this particular theorem. So let's see this question, what they're saying. there exists a differentiable function fx such that f dash x is less than 1 and f0 is 0 and f2 is 2. Okay, just a second. I will come to this question in a while. Maybe I can do this question first. So what they're saying, like by applying the first mean value theorem, or they also call it mean value theorem, or they also call it Lagrange theorem. They are saying by applying the first mean value theorem to root x, show that for each positive integer n, this happens for some c between n to n minus 1. See, what is this mean value theorem says? That in between a to b, if your function is continuous, then you have f dash c and differentiable basically. F dash c equal to fb minus fa upon b minus a. Right? Now, here they are saying this root x. So what is this f dash x? I think it will be. Can anyone tell me quickly? 1 upon minus 1 upon 2 root x, right? No, sorry, 1 upon 2 root x. This will be 1 upon 2 root x, right? Okay. Now what they are saying, that there is a certain point c such that 1 upon 2 root c, 1 upon 2 root c is exactly equal to fb, which is root of n plus 1 minus root n upon n plus 1 minus n. So they are saying there is at least one point c such that this happens. So you are just applying this theorem, right? And then you can prove this particular statement by using the theorem. So by applying the first mean value theorem, you can prove this statement. So basically, it is not always very intuitive that how we can apply this theorem, because that's where they have given the hint that apply the first mean value theorem. But do you think they really have to give you the hint? They just have to tell you that, okay, for root x, tell me that in between n plus 1 to n, this exists. So it is not always very intuitive that where to apply this first mean value theorem. But I hope you understood this particular example, that how we are solving it. Is this okay to everyone? Okay. Now let's just solve this question. And I want you to solve this question before I solve this question. So what they're saying, let f be a differentiable function with two distinct root a1 and a2 basically. Okay, a1 and a2, where a1 is less than a2. Then f dash has at least one root in a1 and a2, which means they are saying कि f के अगर दो रूट्स हैं तो f dash x must be 0. So basically f dash c, if I apply the theorem, it must be, let's suppose I'm applying between a1 and a2. So it will be a2 minus f of a1 upon a2 minus a1, isn't it? Now this a1 and a2, since these are roots of f, that means, okay, can you go from here? How to solve from here? Since these are root of f, then it means these must be equal. Right? So it is basically equal value. So it is 0 upon equal and also 0 basically, not just equal. Since they are roots, they must be 0 also, right? Okay. These are equal and 0 also. Anyway, for us, the equality itself was fine. ये तो Rolle's theorem हो गया, right? It is just like a Rolle's theorem. If f equal to, नहीं, Rolle's theorem तो नहीं. But yeah, I hope you understood. So this is a2 minus a1 and this is given. So it is not 0. So this is 0. So they are saying that there is exists a c such that this f dash c is 0. Okay. Cool. Now let's solve that question, I think. What they're saying, there exists a differentiable function fx such that if f dash x is less than 1 and f0 equal to 0 and f2 is 2, there exists a differential function. I mean, oh, sorry, this is true or false. Okay, sorry, I forgot to write. This is true false question. So let's try to solve it. This is false. Vishnath is saying this is false. How you are doing it? So f dash c you are calculating by f2 minus f1 upon 2 minus 1. So this is 2 minus 0 upon 1. This is 2. So f dash c is 2. What they're saying, there exists a differential function such that f dash x is less than 1 for all x. Okay, this is for all x. So it is not possible because there is a c such that f dash c is 2. Something is wrong. 2 minus 0 is 2, right? 2 upon 1. Okay, divide by 2 minus. Okay. So this is 1. Okay. And then they are saying less than 1 for all x, which is not possible because there is a c such that this f dash c is equal to 1. Right? Good. So basically, actually applying this mean value theorem, the first mean value theorem is not very, very intuitive, but I hope you got some idea. Okay. Now let's just solve this gate question, which is very recent question. And I think there is only just one question they have asked from this first mean value theorem. So what they're saying, suppose f is a continuous random, sorry, not random variable. F is a continuous function on this interval and a is a differentiable function in this interval such that every x in the interval f dash x is less than or equal to 2. So basically, let's just apply this f dash x equal to, in this interval, let's just apply this f dash this is f of 3 minus f of minus 3 upon 3 plus 3, right? So f of 3 is what? It is not given. Minus f of minus 3 is 7 upon 6. Yeah, they're asking what could be the at most value of f of 3. Can you find out the maximum value of f of 3? So f dash x in this interval is always less than or equal to 2. So this is given that this is always less than or equal to 2, right? So maybe I can just write here, just a second. So this is less than or equal to 2. It is given to me that f dash x in this particular interval is always less than or equal to 2. So f3 is less than or equal to 12 plus 7, which is f3 is less than or equal to 19. Which means the maximum value it can take is 19, at most 19. A good question, right? Okay. So I hope now you know that how to apply this particular theorem. Actually, only one question they have asked from this particular theorem. Cool. Okay, you can apply any other method if at all you can have. Now, there are some other questions that we have. If you want, you can solve this question as an homework. So these are really good question. I mean, the solutions are on the next page, but these are really good and intuitive questions also. So these questions are not related to, first of all, the mean value theorems and all. These questions are very nice questions. Like, I mean, I can say, like, I have solved these questions, this type of question in the earlier videos also. So if you want, you can try them out. Okay. So let me maybe just give you some hint and do this midway, and then you can continue later. If two numbers are adding up to 6, so maybe n1 plus n2 are 6, and then they're asking that, can you just maximize this n1 into n2, the product? Okay. So what you can do, you can just replace one of the value, which is 6 minus n1, one of the value, and they are asking what is the maximum value of this, right? See, it was kind of constraint optimization, which means within this constraint, you want to find the maximum value. Okay, but you have converted that to one variable optimization, right? I mean, now you have actually included both of these equations. You have finally formed just one equation. Okay. This is called unconstrained optimization. Anyway, so basically, now you want to just optimize this. Now, what is the value of n1? I think you can differentiate and get the value of n1. N1 will be 3, and since n1 is 3, then n2 will also be 3, right? Then from here, n2 will also be 3. Okay, you can do this, right? Similarly, this is the almost same question that we have. Now, let me just ask you one thing. Okay, currently your graph theory is not covered, but still, let me just ask you one thing. Suppose there is a complete bipartite graph. Okay, graph theory is not covered. You will see that in the graph theory, but still, I'm just asking you. Suppose there are n vertices to distribute. Okay, n vertices to distribute here and here. You may put n1 vertices here. You may put n2 vertices here, right? And total n1 plus n2 is n. And this is a complete bipartite graph in the sense that there is maximum number of edges in between them, right? You do anyone know what is bipartite graph? Actually, don't need to know. You will get to know in the graph theory. But still, I'm just telling you that suppose this is a complete bipartite graph, and then if I just say that you want to maximize the number of edges, yeah, you want to maximize the number of edges will be. Can you tell me? The number of edges will be n1 into n2. If you want to maximize this, then what should be the value of n1? Okay, you can do using the similar method. You can basically put n1 equal to n minus n2 or something, or n2 equal to n minus n1. So you want to maximize n1 into n minus n1, right? If you maximize this, you will be getting n1 as n by 2, right? Okay, so you will see this later, don't worry. Have you seen, do you remember from, if anyone has prepared last year also, do you remember in case of complete bipartite graph, to have the maximum number of edges, we put half and half? We put the vertices half and half such that it is the maximum number of edges. And this is the proof of this, right? You can easily prove this using the calculus. And there are many other applications of this. Of this particular observation. So basically, this is just a similar pattern. This n1 plus n2 equal to n, and you want to maximize n1 into n2, right? The similar pattern we have seen. The similar pattern here, n1 plus n2 is fixed, and n1 into n2 you want to maximize. Similarly, the similar pattern here in this question you can try as an homework. Similarly, like there are, I think, other application is also possible, which is basically, let's suppose that the perimeter of a rectangle is constant, which means, let's suppose the parameter is, I think, 2a plus b, right? This is the parameter. Let's suppose this is some number c, okay, or maybe n, or maybe let's suppose some number 100, okay? Suppose this is some constant number basically, and then they ask you that that if you want to maximize the area, then it means the area must be a into b. Then what should be the value of a and b? Can you tell me? A plus c, from here you can say a plus b is 50. So if you look at this pattern, then it is 25, right? So basically it must be square, which means if the parameter is fixed and if you want to have the maximum area which is possible, then you must be taking the square. Okay, given that the parameter is fixed. Is this understood? Okay, so basically, like, I think there are other observations also. So basically, this is the pattern that I have observed over the time. Okay, so basically, this a1 plus a2 is constant, and they ask you n1 into n2. This is some pattern that I have observed over the time. So I just told you these are my observations only. I told you these a few observations. This complete bipartite graph also was my observation. And what happened, like, before today's class, I was just remembering that, okay, in graph theory there is something. Then finally I got to remember before the class that, okay, there was a bipartite graph. So I was just remembering that there is something in the graph theory, and it's been very I think very much long time since I've touched the graph theory, maybe 4 or 5 years. No, I studied graph theory in ISC, but but okay, that also I don't remember now. Cool. So that is all about this derivative, differentiation, mean value theorems and all. So I hope you are now a bit more comfortable compared to the earlier videos that you have seen. Now we are just left with the integration. So we will see the integration in next class. Okay, you can just try out all the questions that are there in the previous year questions. Okay, cool. So thank you so much. And if you have any doubt, you can ask me later. Yeah. Thank you, Abhay. Thank you so much. Take care. Bye-bye. Bye.